This presentation is about. Can everybody hear me? Yeah, good. This presentation is about the Test Traffic Measurements project we've been doing at RIPE for the last 3 years, and where we're now going from an experimental state into a service that can be offered to anybody who is interested. Okay, on the slide you see the URL of the project, and if you're following this on the M-bone, just beneath there is the URL of the transparencies, and mind you, there's an underscore between the 002 and nanoc. So what do I want to show you in the next 30 minutes or so? Oh, okay, I'm just working on the introduction. Then I'll tell you a little bit about the goals of the project. Next topic is the implementation. Because if you have implemented a thing, you want to develop services and products that people can actually use in day-to-day operations. Show a few examples of those and end with conclusions. So what do we want to do? Well, the goal of the project was and is to determine inter-provider quality parameters. And so far we've been focusing on 3. First one is delay, which is the time for packets to travel from the source. So an ISP somewhere or a user at an ISP somewhere to its destination. Related to that one is the packet loss rate. That's the fraction of packets that send out but never arrives. Third one is the routing. That's the path that the packet takes from source to destination at the IP address level. Fourth one on our list, but that's something we haven't really looked into, is bandwidth, which is the amount of data per unit of time that you can send from one point to the other. Other design parameters. Okay, since we're an organization of ISPs, we want to limit this to inter-ISP traffic only. That doesn't mean that the techniques that I'm going to show you in a few slides cannot be used for traffic on your own networks. They can, it's just that we don't do it. Next thing is that we wanted to do active measurements, where we actually control and generate our own test traffic. That way we're certain what we're sending, and we also avoid all privacy issues related to spying on packets that happen to pass by. We also want to do this one way, so we measure from a source to a destination and not a ping-like thing from source, destination and back. And the reason for that is that there's a lot of asymmetric routing and asymmetric equipment, and if you do one-way measurements, you actually know what you're measuring, and two-way you can always get back to just add up the results you get from measuring from A to B, and you add up the results you get from measuring from B to A. Since we want to be in control and we want to be sure that we're doing the right thing, and people aren't fiddling with our equipment, we have an independent platform for doing our measurements. It has to be well controlled, and since this shows results about how good people's networks are, it has to be well controlled, scientifically defendable. And of course, we're not alone on this earth, so we'll follow the relevant RFCs and internet drafts. So, how do we do these measurements? Well, on the slide you see the typical situation. You have 2 ISPs, let's call them A and B. They each have their internal networks, shown here in green. Somehow they're connected up to a border router. Then there's the red connection, which can be a direct line or can go through multiple people. And you go to the other guy. What we do is we install so-called test boxes, and those are shown here in orange at both ISPs. These boxes are connected to a port of the border router. They have a GPS clock, and I'll show you in a minute why that's needed. And okay, so we have 2 of these boxes, and then we can do measurements. And basically, you measure delay by sending packets from the box at A to the box at B. And here you see the reason why we have a GPS clock. Since it's one way, you have to be certain that the clocks are synchronized, and the synchronization has to be independent of the network. And of course, if you count the packets sent from A, and you can compare it against the packets that never arrive at B. You can determine the loss. To get the routing, you use traceroute. And this whole setup is symmetric, so the box at A is not only sending packets to B, it's also receiving packets sent by the box at B. And you continue like that, and you create a whole mesh. So, what do these test boxes look like? Okay, it's a rack mount PC, Pentium 200, Pentium 233, some memory, a bit of disk space, and even though Pentium 200 is considered an obsolete machine these days, we still have something like 95% of our CPU cycles to spare there. There's a GPS clock. GPS clock looks at satellites in the sky, so it needs an antenna. Up until now, we have had a clock which was mounted in the back of the unit, which meant that we had to run expensive coax cable from a computer room to the roof of the ISP, which was complicated and sometimes not even possible. In the new, we're now moving to a solution where we actually put a preamplifier in the antenna. So you have something that you put on a little plastic dish that you put on the top of your on your roof, and you use whatever Cat5 or whatever wiring there is in your building to get signals down to your computer room. Box is running FreeBSD. It has a special kernel, and for the people participating in this project, it's operated as a black box from the NCC. So the sites participating in the project just have this box. They put it in a rack, they connect it to Ethernet in 220, switch it on, and that's the last they ever had to do, except that we occasionally have to ask them to press the reset button. So this is the GPS clock that's in the back of the current boxes, and actually I'm pretty proud of it since this was the first prototype and I soldered it together myself. And nowadays it's just a simple plastic dish which you put on top of your site. Where are these boxes located? Well, we have 43 boxes at ISPs as of February 1st. At the moment, some 35 of them are taking data. We have a few hardware problems. There's a box is still being installed. And on the left side of the slide, you see a globe, and the red dots indicate where the boxes are. And okay, we just produced this globe, and now it's already outdated. Since for the next talk, I have to make a picture of the back of the Earth as well, since we just installed a box in New Zealand. So we have 43 boxes at the moment, and we plan to double that in the course of 2000. Well, I'll tell you how in a few slides. So now you have this box and it's doing measurements, and what do you get for operational use? Well, the first thing you get is the simplest thing, it's the raw data. If you have a box, you get all the data that's sent by the box at your site or received by it. You can use it basically to do anything you want, but of course we have some data disclosure policies in place, since the data that you get with a box also tells you something about the networks on which your data is traveling, and you can misuse that. And there's this isn't that interesting, so we'll provide plots of network delays and losses, and I'll show an example in a slide or two. We have the routing vectors. We frequently do trace routes that tell us exactly how you get from the box, from the source box to the target box. Those are sort of the basic metrics you can do. And the next thing we're working on are derived metrics. We have networks alarms in place since about 2 months. We're working on summary plots for planning purposes, and I'll show an example of that. We plan to have that fully operational by April. And we have network performance scores. That's basically the next step, and that should be there by about June. And of course, there's a lot more in the data. So we're always interested in hearing suggestions of from people who want to do something with the data. Right. So if you have a box, you'll get access to a web page that looks like this. And essentially, along the left side, you have a column which starts with TTO1, which is the first box, and then goes down for all the other boxes. That's the source. And on the right-hand side, you see a row of targets. And if you click on a random combination, you'll see something that looks like this, which is the performance of a fairly good connection we saw on the net. There are 4 plots in here. Top left is the delay we measured as a function of time of day. And so this plot was generated on March 31st of last year, so it covers the 24 hours just before that. And you see that, so it's midnight to midnight, and you see that the delays were fairly constant. Top right is just the distribution of the delay, so it's all the data points we had during a 24-hour period binned and shown as distribution. Bottom left is a status and control plot, and I won't discuss that. And bottom right is a plot showing the packets that arrived, and you can see that, well, since the whole plot is green, every packet that we sent along this connection actually arrived. Well, this was a good example. We also found bad examples on the net, and here's one. So again, you have top left, that's the delays as a function of time, and you see that it's, well, except for a brief period from minus 19 to minus 15, so that corresponds to 5 to 9 in the morning. Delays fluctuated and are sort of scattered all over the place. And what you also see is that on the bottom right, you have the plot that shows packet losses, and you see that from 9 o'clock in the morning, packet losses for this connection started to go up to 40%. What you can also do is query our database with routing vectors, and we also show the path from one box to another. And changes in these routing vectors often explain changes in the delays. What you quite frequently see is that the delay is constant, and then there's a sudden jump. And if you go back to the IP address level, it's usually related to a router being added or a path had changed. And on the bottom, you just see an example that you actually get by querying our database. So January 29, with a connection with 9 hops, and that worked. And on February 3, the delays had suddenly gone up. And if you then look at the trace routes, you see that there is an extra hop introduced, and the path is slightly different. And that brings me to my next point, so-called delay alarm. I mean, it's nice to see these plots of delays, but that's yesterday's data that has some interest. But you also want to know when something goes wrong and packets are completely lost or delays suddenly go up. And delays, one of the reasons delay go up is that instead of the regular path, something is broken and it's taken some back route. So that's why we have developed an alarm, and that's shown in this slide. You should start by looking at the left plot. You see the delay for a 24-hour period, and if you look just above the red arrow, you see a jump, and this is minus 20, so that's 4 in the morning. And this is a performance change. Of course, we're not in control of the networks, so we don't know what happened, but if you're hosting a box, you probably like to know that something broke or the net is suddenly getting a lot slower. Then you also see a peak sort of that's basically the peak shown in between the green bars, and that's not an alarm. That's something where people come in, since this corresponds to 9 in the morning to 5 in the afternoon European time, which is basically the time that the users of the network are using it, thus putting traffic on the link and thus increasing the delays. And the alarm that we have will trigger on these sudden jumps, but it won't trigger on day-night effects and other usage patterns that we can sort of predict. So this is how we do it. We basically calculate median and percentile delays, and we compare that against the previous days. And as soon as 95% of the delays are outside the expected range, we'll raise an alarm. And at the moment we do this by email. We're planning to move this into SNMP later this year, so that it can be put into whatever monitoring system you have at your NOC. Of course, besides setting the alarm, we also clear it if the unusual condition disappears. At the moment we have a response time for something unusual to happen of about 15 minutes. This is something we can still tune. We can make it as short as you like, but the consequence of this is that you'll get more false alarms. So it's tunable, but at your own risk. So this is just the typical message you get. Okay, I believe you have all seen the emails before. We've now been running this for the last 3.5, 4 months. What we typically see is that there are 6 alarm set messages for each box each day. Most of them, if we look at the plots, are actually real effects, so it's not just a little statistical fluke. We're still in contact with the sites that actually get the alarms, get some feedback if what we saw actually correlated with their techies playing with the networks. In general, people seem to like this more than getting angry with customers on the phone because the net is so slow. And like I said, this is a tool to detect short-term network performance changes. So what about long-term then? Well, the other question you probably ask is, how do delays develop over time? I mean, does the network get slower? And if it gets slower, how fast does it get slower? And when should we buy more bandwidth? This is typically things that develop over months to half a year or a year. And at that point it becomes hard to look at all the individual measurements, since you have hundreds of thousands of data points. You want to make a plot, okay, that takes a few minutes. You see that it's not exactly what you wanted, so you fiddle a little bit with your script, you run it again, and you wait for 5 minutes, and that's, after 2 or 3 cycles, you're just bored. So what we do then is summarize the thing. We summarize the data for 6-hour intervals in percentiles, and we define 3 percentiles, the 2.5% percentile, so that's the lowest, the delay corresponding to 2.5% of the measurements. This is sort of the best case, and it's roughly equal to the line speed between source and destination. We also calculate the 50% or the median, which is sort of what the average user will see, and the 97.5 percentile, which is the worst case over a day. Now, if you do this, okay, you reduce all the data to 12 numbers for per day, or still a handful for each month. And these are things you can much easier play with. So what we're doing at the moment is actually plot them over time. And this is the behavior, the median behavior you see for one of the connections in the month of October. So yeah, the plot has to be polished up a bit, but basically the x-axis is Unix time, and on top you see in red the days. So it starts at October 1st and it ends on the 31st. On the y-axis you see the delay, and the black, red, green and blue points corresponds to the various intervals on the day. What you see here is that it started, network ran fine on October 1st, delays were in the order of 50 milliseconds, ran for 10 days, and on the 10th of October something changed, and it wasn't just a temporary hiccup. No, it was an unusual network condition that continued for, well, until the end of the month. And well, yeah, there are two things you can say about this plot. If this is a real effect under your control, you might want to change equipment, or you might want to look at why things broke. And if this appears, as soon as your network appears to be okay, but you have some upstream provider, you might want to call him and ask him what happened. So these are, and you can also look at this in a projection, and then of course you see two peaks. And besides just providing the plots, for a typical site, you would still have to look at 200 plots. We're also playing a bit with algorithms that detect this situation from a situation where you just have one peak, so the behavior is more or less constant over the period of a whole month. Next thing is network performance scores. Well, why do we want to do this? Well, if you have a test box at your site, and there are hundreds of them elsewhere in the world, it means that you have 200 connections, and thus you have to look at 200 plots, and we have several plots, so it's a big pile of paper. And if you want to look at this on a daily basis, it's a lot of work. And if you give this to your manager, he's probably bored after looking at the first two plots, and he just says, okay, what's the summary? So we'll just create one number. So we're working on a scoring method for network connections, where we've artificially said, okay, if you have a perfect connection, we'll give you a score of 1,000, and perfect means no packet loss, minimal delay, that is, given the distance between the boxes. Obviously you cannot go any faster than the speed of light, and a little variation in the delays. So day or night, the delays are about the same, and your network isn't congested. And of course you also have a score of 0, which means that there's no connection at all, or it's just unworkably bad. And if you play with it, you can come up with a formula like this for a score between 2 points, which essentially, okay, I won't explain this since I'm running out of time, but essentially it's three contributions: a loss contribution, a delay contribution, and a variation in the delay contribution. And okay, we're still tuning this. This is something where we're going to calculate daily and compare against previous results, and then provide you with a list for the individual connections, and then do the average for all the connections you have. So you have the score, and you don't have to be afraid that this will end up in the newspaper. Sort of XYZ Internet got a score of 2, and its competitor got a score of 10. Now these are numbers that will be made available to the hosting sites only. So, okay, that's the web page. So that brings me to my last point. What if you find this interesting and you want to host a test box? Well, that's going to change, and it's going to change for the better. So far, This project was funded from the RIPE general budget, so we were limited to giving the boxes away inside the RIPE community only, and we had to put a limit of 1 box per site or 1 box per member. Well, most people have more than 1 pop, so they want they might want to install a box at each of their pops or whatever. And there's also some interest outside the RIPE area. Well, so as of April, anybody who is interested can basically call us and buy as many boxes as he or she likes, because with the restriction that we should be able to produce it. Now, boxes, the model will be that you pay once for the box, and one of these test boxes is about $2,500 US, and you'll also pay us a yearly fee. And I'm afraid that I cannot give you a number on that, but it will be something of the same order as the price of a test box for operating it from the NCC, running the analysis codes, provide you with all the numbers we showed you on the previous slides. And in parallel with that, we also will offer a possibility to do private experiments. So far we've always said, okay, we have this mesh of test boxes, and we just measure on this full mesh and show everybody the results. Some people might want to say, okay, I have 5 pops and I just want to measure between my 5 pops. And yes, that's possible then as well. Details, and this is mainly political and stuff like that, will be discussed at RIPE 35 end of this month, at which point, well, if you're on the RIPE list, you'll see the announcements appear. So, to conclude, I've shown that we have a setup to measure network delays and packet losses. We have products for daily use, and we're always looking for more sites interested in hosting one of our boxes. And just to finish off with the contact information, project has its URL, it's above. If you want more information, just contact me. And if you want to participate in the discussion about the development of this project, you can subscribe to the major donor lists hosted at the RIPE-NCC for the working group inside RIPE that discusses this project. And with that, I'd like to open the floor for questions. Thank you.
Randy Bush, Vario. First of all, I'm a satisfied user. Just want to say that this is pretty neat stuff. It's good computer science, it's good operations, and it actually does useful things. Secondly, there's a warning which I do not think can be sufficiently stressed, which is the box requires an antenna. And for those of us in POPs, in carrier, what are called carrier class facilities, hopefully they're a little better than that, this is exceedingly difficult.
Yeah, that's why we're moving towards a different clock. And
right.
Basically, now if the thing works as we think it works, and we're in the process of testing this, all you have to do is have access to the roof and the possibility to run Cat5 from the roof.
All you have to have is access to the roof.
Yeah,
is a major problem and involves legal departments and contracts and horrible things that we shouldn't be thinking about.
I agree.
It's not your fault. Yeah. It's not a blame thing. I just would like to, I think it's fair to warn people who want to play that that's the big obstacle. Everything else is cruising. The RIPE crew is wonderful. They're easy to work with. The technology is great. The boxes are solid. It's getting to the roof is hell. And then there's a problem, Henk, in scaling, and I'm wondering how you're going to approach that. It's that the boxes themselves are not self-sufficient. In other words, my box does not have the website that I can go to and it tells me how it's doing talking to all the other boxes. There's a centralized facility where the data are collected and massaged, and if this becomes popular, which I hope it does, what are the thoughts of the different ways to be able to scale that internationally? And one suggestion that I've made in the past is to start a conspiracy of operators over here to help break it into two pieces at least across the whatever. I mean, what are you folk thinking on that? And I will be in Amsterdam in 2 weeks or whatever to whine about it there too.
Yeah, I think our web server as such can handle all the data. Processing. I mean, that's something we're thinking about. At the moment, we have one big Sun machine processing it, and at some point we'll have to parallelize that and just buy a few more machines to do the processing. And where we do this, I mean, if we just stack all these boxes at the NCC or put them in various places all over the world is still to be studied.
There was someone. Hey, Henk, thank you so much.
Okay.